Okay, so we're going to look at the shaders a little bit here. We have some lighting calculations already inside the current shader. We have a sphere here lit from one side, and there's a video online that you can follow if you want to be able to set your shader up the way it begins here. But the idea is we're only lighting the sphere up with the diffuse lighting, the lighting where the position of the light and the direction of the normal of the object has an effect. The position of the camera has no effect, and there's nothing else. So the intensity of this light is controlled by the relation between the direction to the light and the direction that the object is facing on each spot. So if we look at this sphere here, we can imagine that right here where it's brightest, we have a normal that's pointing right out of the side of the sphere. And if you look over to this side, the light is somewhere around here. So the light coming from this direction will hit the normal that's here, where the normal is pretty much straight out, so that they're more or less parallel. The direction to the light and the direction of the normal are more or less parallel. And when they're more or less parallel, then their dot product divided by its lengths will be high, which is the cosine of the angle between them, and the intensity of that will be high, giving 1 if they're exactly parallel. But on the other side here, if we look at this spot here where it basically fades out to black, we imagine the normal is pointing straight at us. The way the camera is set up here, the normal is pointing straight at us, but the light is still coming from the side here. So imagine there's exactly where it becomes black here, we have a 90-degree angle between the direction to the light and the direction of the normal. That is the direction that the surface is facing, and so we get no intensity of the light there. And if we look at the shader that does this right now, we've set up two things here. We've taken basically the shader specific code and put it into this class shader, where we're affecting all these variables. And what this does is it simply gives us access to the variables of the shader. So we can look at that later on, and we can go through that. But the main thing here is this class allows us to put data into the variables of the shader. The shader itself is this code here. So the shader itself is simply a small C program, except the shader language, it's based on C, but it has some specific functionality that helps us make a lot of these calculations easier. Like all of the multiplications of vectors and multiplications of matrices and vectors are really simple to set up in the shader, simply with multiplication signs. And then we have these specific variable types: vector 3, vector 4, material, or matrix 4, sorry. And we have matrix 2 as well, which is a 2 by 2 matrix, matrix 3, which is a 3 by 3 matrix, matrix 4. So we can set up a lot of types of shaders with this. So the variables here, the uniform variables, are what we are given access to through the shader class. So we can put data into these. And right now we have the model matrix, we have the view matrix, and we have the projection matrix. And we've looked a lot at the functionality of what that does, and how we are basically multiplying our positions and our normals with these matrices, and more or less bringing them here to global coordinates, to I coordinates by multiplying with the view matrix, and finally to clip coordinates, which is what we send eventually into GL position, which takes it along into the rest of the OpenGL pipeline by multiplying here through a projection matrix. So we've set these ideas up already, but what we're going to look at now is how we can manipulate the color inside the shaders as well. And to begin with, the idea here is that we have these varying variables here. So a variable in the shader that is varying is a variable that we can set, and OpenGL will bring that variable along with the vertex, with the clip coordinates or the current coordinates of the vertex, throughout the rest of the OpenGL pipeline. So uniform variables are only used within this shader. Attribute variables are the lists, the vertex lists and the normal lists that we're sending each time. So when we change uniform variables, we're basically changing the state of our shader, changing the data of our shader, but that's static data that's in the shader. Every time we actually want the shader to run its main function here, we send normal lists and vertex list into it. And when we send these lists, OpenGL will take each position and each normal out of those lists, so the first of each list together, and send that into this main function. When that's done, it'll send that on into the OpenGL pipeline and then take the next position and next normal off of our vertex lists and send that into the main function. So for each vertex that we're going to draw, basically each corner of a box or each vertex that we've defined as part of the surface of a sphere, for every single vertex, the main function of the shader is called once. And what we can do is that for every vertex that's sent through the pipeline, we can send along with it as many of these varying variables as we want. In this case, the only thing we're sending along is the color. So we're basically saying in this vertex shader, we're going to calculate the color, and then we're going to basically link that to this vertex and say this vertex will go on through the OpenGL pipeline as GL position, which is these base clip coordinates of the OpenGL pipeline, but linked to it will also be some color. And that color will come into effect again in the rasterization and in the fragment shader. We can look at our fragment shader here. I think we have that here as well. So our fragment shader is super simple. It simply says the color that we calculated in the vertex shader, after it's been basically rasterized onto the pixel. So it's not the exact same color, but it is a weighted average between the colors of the vertices in this polygon. So basically, you can imagine that we have the vertex here, we have a triangle, we have these three vertices which are part of this triangle, so B1, B2, and B3. Each of them has this color, which is this varying variable that we made. And if we make more of these varying variables that we want to calculate, we can hang those on as well. So we can, put vectors and stuff, or other colors, or different types of color that we want to manipulate differently. So that's basically hanging on to these vertices. What the rasterization does then is it goes through all of the pixels that will be rasterized, that this triangle will be rasterized onto. And for each one of those pixels, it'll say, I'm going to take some weighted average between whatever you put in as a varying variable here. And that's the color that I'm going to give you into the fragment shader. So the fragment shader will get some color for each pixel, which is a gradient or a weighted average of the colors that we calculate per vertex. And that's the color we get here. So each fragment will have a different color. And we can see it if we run this. This sphere here is made out of a lot of polygons, but we don't really see the polygons because for each corner of each polygon, a color is calculated, and that color is then kind of made into a gradient over the entire surface of the polygon, meaning that we get this kind of smooth gradient over the entire surface of the sphere. Okay, so that's the idea with the shader. We're going to calculate a color in the vertex shader, and that color will be part of the vertex throughout the pipeline, and we can access that color again in the fragment shader for each pixel. So we calculate it for each vertex, but we can access it for each pixel again here. So what we're doing right now is that after we've done the matrix multiplication with the model matrix and we're in global coordinates, we have access to the position of a light, the diffuse factor of a light, and the diffuse of a material. Before we only had just a single color, which is the color that we just put onto everything that we drew. Right now, we have a position of a light, we have the diffuse of a light, and the diffuse of a material. And what we want to do at this point is we want to be able to say, every time the main function is called, I know I have access to a specific vertex and a specific normal to that vertex. So that data I can use to calculate the direction to the light first, which is this vector s here. So this vector is direction to the light. What we do next is simply what we looked at when we were learning the lighting calculations themselves. We say if we have the direction to the light and the direction that the surface is facing, which is the normal itself, we can take a dot product of those and divide it by their lengths, giving us the cosine of the angle between them, and that's the intensity of how the light hits this surface. That's not the color itself, but it's how intensely does the direction of the light affect this surface. So that intensity we put into this Lambert factor here, and then our color will be the diffuse color, which is a vector here with red, green, blue, and alpha, are basically our diffuse part of our light, the diffuse part of our material, and then multiplied with this. So the lower Lambert is, obviously the more we're attenuating or the more we're shrinking the diffuse parts themselves, but the color will never be higher than the basically combined diffuse factors of the light and the material themselves. So if we just look at the values that we're putting into this, so we say, see V color equals this, and then we do nothing more to V color because V color is varying, and we can access it again in the fragment shader. So if we look a little bit at the data that we're sending into this, we can go into the display function of our main game here, and see here I'm setting the position of a light. So we can see pretty much just by going in here more or less where the light is coming from. We have the diffuse factor of the light, which for now is just 111, so it's a completely white light. And for this sphere that I'm drawing, I'm setting some color here. We just try to put that to 111 as well. We can now see that when we multiply these together, we have the material diffuse and the light diffuse. We multiply these together, and what the shader language or the shading language does when we multiply vectors together, which is not something that you can actually do in linear algebra usually, it does it component wise. So it multiplies each component together, and then it makes a new vector with those components multiplied. So it doesn't take a dot product and end up with one number. It actually multiplies the first coordinate of this vector with the first coordinate of this vector, and puts that into the first coordinate of the resulting vector. Then it does the same for the second coordinates. So we can actually multiply together vectors and get a vector of the same length with each coordinate multiplied. So that's nice to use in the color calculations when we are using the vectors to hold color values. Whereas when we're actually doing the geometrical transformations, we want it to work like regular linear algebra. And when we actually have a matrix as one part of multiplications, if we're either multiplying two matrices together in the shading language, or we're multiplying a matrix with a vector, or a vector with a matrix, then it works like regular linear algebra. So it does a regular matrix multiplication when one of them is a matrix. When both are vectors, it does it component-wise. And when we actually want a dot product, which would be a more normal multiplication of two vectors, it's basically like taking one of the vectors as a row vector, the other as a column vector, and multiplying them together. then we simply call dot between two normals. So we get the dot product like this, we get this component-wise multiplication like this. Either way, the values that we're putting in here, 1, 1, 1, will be multiplied with 1, 1, 1, so the resulting vector here will simply be 1, 1, 1, 1 again. So the only thing affecting, with this setup here, when we're sending this in here, the only thing affecting the color now will be this intensity Lambert. So if we were to simply remove Lambert here, y array index out of bounds exception, or did I do something wrong? Draw solid sphere. Okay, the shader must have, let's go back into the shader. Sometimes the shader won't properly okay, let's try something else then. I'll figure out what exactly was going on there. I'm not sure right now. So let's try something else. Let's say Lambert just equals 1. Something about what we're putting into the color at this point is not... Can anyone see if I'm ending up with numbers here that would be higher than... that would be higher than 1 or lower than 0? I'm not getting compilation errors on the shaders themselves. I'm getting these warnings here, but that shouldn't matter right now. We put something else in here. It's not Java. So it's just Java. This would probably simply give me a compilation error. So this is working nicely. Well, what I was gonna do was basically just end up with a flat lighting on the entire sphere, where everything just ends up as 1. Okay. Alright. We have S here as well. I'm going to see if one thing could fix this. Let's take Lambert out here. Take those lines out. No. Light position is now not being used. Okay. There's one thing that the OpenGL, it's a nice place actually to mention this. The OpenGL shader language can be a bit weird with that when it's compiled. If you define a variable here and then don't use it anywhere in the code, the compilation will actually just omit the entire variable, which means that when you start to try to access that variable from outside, like from our shader class, we can get null pointer errors, or when we actually send stuff in, things won't compile. So what's happening in this case, maybe I actually want to see if that is the case. So vector S equals this, float Lambert equals this. I'm going to see if I can just add Lambert now equals 1. I'm not entirely sure how clever it is with realizing that now I'm just kind of bypassing code that would otherwise. So is it realizing that there's no use for S here? Weird. And we can do something like min between 1, or no, max between 1 and this dot product. See if it compiles like that. Okay, it compiles. So the error here is actually, and as interesting as that is, the error is that the compiler is clever enough to realize when I'm not using a variable. And if I just go down here and say, now I'm just going to put Lambert to 1 after this, it realizes, okay, you're putting Lambert to 1 here, which means that this line is unnecessary. So I'll just omit this line. And if this line is unnecessary, you're not using the vector S, so I'll omit this line. And if the vector S line is unnecessary, then I'm never using light position, which means I'm going to omit light position as a variable in this, meaning that when I try to run the shader and I'm sending this data into it, like light position, it'll actually crash because I don't have any handles to data that I'm trying to change in it. Anyway, let's not dwell on that too much. But this makes it a bit difficult to work with this because it doesn't give any compilation error. So if I'd actually do something like, I'll just make something wrong here. See, I'm getting an actual compilation error on the shader here. And if we want to look at where I get that, I can go into the shader code. And after I compile these shaders, I can call getShaderInfoLog with the shader ID, and I simply system out println that. So if you're getting weird errors on your shader, it's nice to actually see if there are compilation errors. But also make sure, whenever you're using your shaders, that there are no unnecessary lines, or if you have, don't add variables to the shader and start trying to manipulate them until they're actually being used in the code. But okay, back to where we were looking at this. So now we're simply setting us the same color to every single vertex, just to get an idea of what OpenGL does when I just put a flat color to a sphere. It doesn't matter, it's rendering it in 3D. We don't really see any 3D going on here because the colors aren't changing. And the entire thing, both the pyramids. What's happening now is we're simply taking the value 1 and multiplying that with the light diffuse and the material diffuse. And for the sphere, the values in material diffuse are 111, light diffuse are 111. So what we end up is the color 111 every single time. So if we look at the difference between taking the number 1 and multiplying with that, and taking the actual intensity that we get, now we have this. So you can see that the color that we're calculating per vertex is differing depending on in which direction the light is. And if we now do something like saying, let's look at where the light is now and change it. I've set this up so that it has the same center position here. Let's not do that. Let's take the position of the sphere as its center, which is 0, 4, 0, and then I have this cosine sign making it go around in circles, and we'll just have a circle of radius 3. So let's see how this looks. Okay, so now the sphere is still every frame being lit from the side where the light is. You can also see on the very intense kind of central white there that the light is a bit closer. And if we just zoom out a little bit further, we can see on this pyramid how the light is always sort of lighting it from this side, but just as it goes here, it kind of enters into the pyramid, and so some of these walls are lit from the other side. And if we look at the other image here on the right, which is doing this top down, we can also see how the light is kind of moving through this. So now I'm manipulating the position of the light, but we still just have white light and the white material. Now, so I'm doing it on this image here on this side, and if you follow the mouse cursor, it's more or less exactly where the light is.
Like away from the ball, is it the light coming from the ball?
No, the light is where I'm at. You can see the light is now here, and it's lighting the ball. So if we stop this spinning motion, and instead just put the light to, let's just make it 3, 4, 0. So, okay, now I can see that the light is, if we look at the top-down image here, the light is exactly here. And it's lighting the sphere from this side. Or if we go on this image, the light is here, lighting the sphere from this side. So the light isn't something you see. You can't see the light. The light is just a light source, and things are lit from it. If you actually want to put a light source that you see, you're going to have to actually render an object with some color. Then you'd probably try to use just flat color on that, like the white color that we put on the sphere earlier, where it's just completely lit white. That would be something you do to an object that you want to be the light source. But the light source you can't see. The light source is just the direction from which the object is lit. But a light source isn't an object in itself, and you can't see it. You only see it by where the object is lit from. Okay, so if we go back into letting the light spin here, you can see it both from above and from the side. The light is moving around here, and so the sphere is still all the time, and the sphere has the exact same vertices facing the exact same ways. The difference is that the light is moving around. So the intensity, if we go into the shader again, the intensity of Lambert will change, not because the normal is changing or because the position is changing, but only because the light position is changing. And when the light position changes, the S vector changes, and when the S vector changes, the dot product will change, and thus we'll get a different light, basically lighting intensity in each frame for different vertices. So is this sort of solid? Are there any questions you'd like to ask? Because it would be nice just to have it very clear that we understand how the light...
If you have a Lambert at 1,
yeah,
and change the light diffuse and material diffuse, does it affect the final color, or will it always be black?
If I just do what we did earlier again, so I'm just fixing Lambert to 1 here, so we will get exactly white on the sphere,
Yeah.
but we get other colors on these things because I have another material on those. So if we now go, yes, the light diffuse will change it. So if we now go ahead and change the light diffuse in here, so we're setting the light diffuse to 111. Let's set the light diffuse, we can actually set it to this weirdness here. Okay, so the material here is still white. This is entirely white sphere, and the light intensity is always 1 because we just imagine that the light doesn't have a position, it's just... But the light diffuse, so what we're doing here doesn't really have any counterpart in reality that we're simulating. But that's the thing about this. It's, in the end, we can do whatever we want inside this shader. I can just do whatever math I want and end up with some weird number, and that's what I put onto the vertices, and that's fine if I want to do that. But the idea that we're looking at here is we want to kind of simulate some kind of reality in our lights, and so we're taking this dot product in order to have some intensity based on the direction of the light and the direction the material is facing, or the object is facing. Then we take the light's diffuse, the material's diffuse, and this intensity. And right now, we're still changing what? The light diffuse. but now the light is actually moving again, and we're calculating the Lambert intensity and not just making it flat. And since this is the light diffuse that we're changing in this way, we can see it affects, these colors affect all of the objects. They're all changing color weirdly. If we, however, go in here and say, so okay, this is the light diffuse I'm setting with these weird numbers. I'm now just going to put the light diffuse to 1 again. But instead, I'm going to take these weird numbers and put them on the material diffuse. This will only be the material diffuse for this solid sphere, because when I go in here and start drawing the pyramids, I'm setting another material diffuse. So each of the pyramids will still have their color, but the sphere will be changing its material. So you can see the sphere is still doing this weird color changing thing, but the light is white, and we can see that because the same light is affecting the pyramids, and they just have their fixed color. So once we have different diffuse colors for the light and specular colors and ambient colors for the light and the material and shininess, this is going to be a lot of numbers that you have to change around, and it gives you a lot of power, but in a sense it also gives you a lot of confusion. So right now let's change the materials just back to white. Where was that? Here. So okay, material diffuse back to white, and so the diffuse color is more or less something that we kind of understand now. Just doing this little calculation to simulate this intensity, and probably have some weird stuff in here. Here, just erase this. I think. So the idea here, if you just draw the image up again, is that, so the idea here is that we have this sphere, and at some point in this sphere we're drawing this vertex, and the sphere isn't an actual sphere, it's made up of straight polygons. But at some point we're doing this vertex, and let's imagine that it's part of this here polygon, and it has a normal that points here. Then we have some light that's positioned here. The light position minus the position gives us this vector here, and the little Lambert intensity is the cosine of this angle. So if the light is here, it's lighting the surface from straight on, it gives us high intensity. If the light is here, we get 90 degrees between here and we get entirely black. And so if we have the light positioned here, this will be of moderate intensity. This normal here will get high intensity, or this vertex here. They're part of the same polygon here. You can see that this polygon here is part of the same polygon. So we'll get high intensity on this end, lower intensity here, but through the fragment shader and the rasterization, the fragment shader will get every single pixel which is part of this polygon, and it'll get some kind of average between this high intensity color here and this low intensity color here, and we'll get a gradient between that, which is the final result. Two light sources. If we have two light sources affecting the same object, we will simply do this calculation for each of them and then just add them up. Just the color from light source 1 plus the color from light source 2. So in the end, we take, so because each of those light sources will also have a different diffuse. So we'll calculate Lambert for the first one, and then we'll make some, well, we can actually put it into V color and then just end up here somewhere with V color plus equals, and then Lambert 2 Lambert 2 times light diffuse 2 times material diffuse, because obviously it's two light sources, so it's a separate diffuse color for each light source and a separate Lambert for each light source because they have different positions. So we have to calculate the vector S for the second light source, calculate Lambert for the second light source, multiply this up, but it's the same material that's being affected. So a shader that allows for more than one light source, which is what you need to set up in the end, will either need to have just duplicates of these variables for light source 1, light source 2, light source 3, and then maybe some Boolean switches that you can use to switch on and off each light and say I'm now using 2 lights, but now I'm using 5 lights, and I'm using, so switching off different lights. And then the calculations will simply have to do these calculations multiple times. Or you can make some kind of vector of light sources. And you can make little structs here inside the shading language, make a struct for a light, and then make a vector of that, or an array of that struct, and then walk through that array, basically in a for loop. And that loop would do these calculations for each light on the material and add them up as it goes along. And the final color will be the sum of all of those diffuse light colors for each of the lights. Then we add to that specular for each of those lights, and then we add either the ambience for each of the lights or a global ambience multiplied with the ambience factor of the light, and then we can add the emission. So a full, if we're going to copy exactly how the fixed OpenGL pipeline works, we'd basically have 8 lights, 8 fixed lights, and we'd have specular and ambient and diffuse for each of the lights, and the material would have specular and ambience and diffuse and emission, and then we'd have a global ambience factor as well, and we'd have to sum all of this up into one. So did that answer the question, or did it over answer the question? Okay, so what was I changing here? Okay, so we're just working with one light source now, but if you add light sources, you just do the same calculations for the other light source, and then you add the resulting colors. So I wouldn't actually use V color until the end, but do something like vec for color 1 equals this, and then do the same for the next color, and then end up saying V underscore color equals color 1 plus color 2 plus color 3, so on and so forth. If you have fixed light sources, which is much simpler, I think, than trying to implement them as kind of an array of structs, which can be a can of worms, actually, especially because you have so little kind of compilation feedback on your shader. You kind of want to make sure that you're making small changes to it, so you don't have to go bug fixing much inside the shader, because that's going to be a very difficult thing to do, or it can be. All right, so I'm just going to see if this still works. Nope. Okay, out of bounds. I'm doing something wrong now. Yes, color 1 doesn't exist. No, V color was never set. That's the V color here. Okay, so that's nice. Let's fix the light to a position again. Yeah. Fixed position for the light, and let's look at specular lighting. So this is diffuse lighting. And diffuse lighting is affected only by the, let's just do a lot of this. End up with pretty much just the one, okay? So specular lighting is affected only by the normal. Let's call M, I think, in the calculation. So the normal to the surface, and the direction to the light, which is the vector S. Specular light, however, is affected by both of these things, but also the position of the eye. So we have the eye here, and we can calculate a vector v, which is the direction to the eye. And now what we want to do is we want to say we want the highest intensity of this when this normal m here will reflect the light straight into the eye. And the way we did this was we took the halfway vector, the vector h, which equals v plus s, or s plus v. Great. V plus s. I'm trying to erase here now, but it's not giving me an easy time with that. Okay. So h equals s plus v, and this halfway vector would be the vector that would reflect the light straight into the eye, or at least a good approximation of it, or good enough for us. So what we want to do is we want to say, if this were the vector that would reflect the light correctly into the eye and give us highest intensity, what's the angle between that and our actual normal? So if our actual normal m is actually parallel to this vector h, we get the highest intensity. If our vector m is further away from that, we get lower intensity. So let's just do this together here. If we look at our shader now and the information that we have, what more information do we need now into the shader in order to be able to do these calculations? Can anyone see that quickly? Okay, we need the position of the eye. So we don't have that here. So we need to find, let's stick that in here and say uniform vec4, just call it eye position. Okay, so we've added eye position here. Now we need to use that in some calculation, but we also need to access that in the shader. So let's start by doing that and say, okay, that means we also need a eye position location. We need to duplicate one of these and say, so we had uniform eye position, and this was the eye position location. Okay, so eye position location gives us a pointer to this. And finally, let's go ahead and make a function like this as well and say set eye position to xyz, and this would then affect the eye position location. Okay, I think this should be all we need. And finally, let's set this somewhere here. We don't really, well, yeah, if we're changing the camera around and moving it around, we're going to have to do this for each frame. So we're going to do it in the display function. We've set the view matrix, we've set the projection matrix. Let's go shader dot set eye position to cam dot I dot x, no, cam dot I dot x, I z, y, z, and this will simply be 1 because it's a point. Okay, so now we're doing this, and let's do the same for orthocam, because it's not, as we don't want the intensity, the highest intensity for the specularity to be on the same place in the sphere for both of the cameras. We want the cameras themselves to look like they're affecting how the light reflects off of it. So I think we have everything we need set up here except the actual calculations. So if we look at these calculations here, let's save this. So we have the vector here. What do we need now to make the vectors that we need? So we have the eye position. If we look at this image again, this very, very clear image, what are the vectors that we don't have? We've already calculated S. So we need H and V. We need V first in order to calculate H. So the vector V, you can say vec for V equals what then? Yes, U underscore I position minus position. So again, it's the direction from the vertex that we're working with, which is the position that we're working with here. We could call this position vertex position to make this clearer, but okay, so this is the direction to the camera. So we're going to do this Phong shading model for the specularity. There are other shading models that you can go and look up on the internet and do a little bit different calculations, but we're going to go with this for now. And the Phong shading model uses the H vector, which equals S plus V. And finally, what do? I want to make the intensity for the specularity. So Phong equals, it's going to be a dot product again, because we're looking at the cosine between, or the cosine of the angle between two vectors, except now it's the vectors n, or normal, and h. I take the length of h as well. Okay, so now we've calculated this. What do we want to add to here? So now we're using the light diffuse and the material diffuse and Lambert. We have Phong, but we don't really have specular values for the material or for the light. So what I'm going to do here is I'm going to allow myself a simplification of this lighting model, and you should definitely experiment. You just have to add variables for the specularity and read those in. But for now I'm going to say we have Phong, and we're going to multiply that with, just going to use the light diffuse as the light color. I'm going to use the same diffuse for the light. Then I'm going to multiply it with vec for 1, 1, 1, 1. So I'm going to say, regardless of the diffuse of the material, that is what the color of the object actually is, I'm going to imagine they're all shiny enough to reflect white light. So the light that reflects off will be white. This is a very simplified model, but I'm going to see if the effect of that is nice. In the end, you're going to want to be able to either have separate specular and diffuse for the materials at least. In some cases, you can say the light just has a color, and that color is used for both specular and diffuse. A full light model would have separate diffuse and specular for lights and separate for materials as well. But now I'm going to imagine that the specular of the material is just fully white, but the specular of the light is the same as the light color. And then we have Phong. We're not quite there, but let's see if we get something happening and not just a crash. Okay, this is pretty intense specularity. And we are doing something wrong here. Because the normal between h equals s plus v, we're taking the length of h, I minus position, and we are setting the I position here to cam I. I'm wondering, is the specularity on any of this changing when I'm moving around? Yeah, it is, isn't it? It's hard to see it sometimes on the sphere. I'm wondering if it's easier to see it on the top view. So look here. If I move around, it's hard to move in correct directions. If I move to here, we can see that the specularity point there is kind of changing. Just want to make sure that we're actually having an effect on. So if we go above it, for instance, specular light should be following us a little bit. There you can see that it's reflecting off of the sides of the walls differently. Okay, what we want to add though, and after we add that it'll be a little bit more clear. You can see that this specularity here doesn't really look like anything shiny. It just looks like everything's overlit and weird. So what we want to do is, while the diffuse light is nice when it just lights half of the object from the side, most intense on the very end, but then a little bit less, what the specularity should do, or we feel that it should do, okay, here we have diffuse. So it's nice to see that the diffuse lights this entire object. For something to look shiny, it doesn't really look normal that the shininess kind of reflects off of the entire object. So what we add to our vertex shader now is we're going to add one floating point value here. So uniform float material shininess, and then in our shader we're going to have to add that as well, material shininess, shine location. Let's take that as well and say where we're putting the material diffuse. Let's take material shininess and material shine location, and make set material shininess. We should actually just be able to say set shininess. And then GL uniform F, no, GL uniform 1F, material shine location and shine. And then let's go to here where we set the material diffuse. Let's just add it here below. Shader dot set shininess. So let's try something like 10 to begin with. Then we go into our vertex shader and we need to use that shininess. And what we do is we say Fong should actually be set to the power of shininess. I'm pretty sure that's the syntax, if I remember it correctly. No. Shininess was obviously underscore material shininess. Okay. So this looks a bit different. Does it look up here? And where is the sphere? It doesn't really. Okay, so it's interesting to look at the sphere because we see this point here. We can actually make it even smaller. So let's set our shininess to something even higher, 20. The higher Okay, so if we look at it in this image, for instance, you can see that the position, oh, it always goes out of it, kind of changes. Okay, and you can see that the shine point here is following me around. So even when I go a little bit behind where the diffuse is already black, I'm still getting a little bit of shininess because the light is somewhere here and then it's reflecting off of here and into the eye. So I get a higher intensity there. When it adds up onto where the diffuse intensity is highest, obviously you get a very ridiculously strong intensity. Everything is a little bit wider on the projector as well than it is here in the computer. So if we actually say now, I'm going to take the material diffuse and make that a little bit darker, and maybe put a little bit of color on it, a little bit blue. Now we actually start seeing the vertices again, right? Because we're calculating this color for each vertex, and then it's just being linearly graduated over the entire surface of that. And if we actually go into our sphere graphic here, this can be even more obvious if we make the sphere less detailed. You see here I get no specularity, which is ridiculous, and then it happens here. Okay, let's save that for when we have time. Great. Okay, let's put it back to, well, let's put it even higher. Let's just make it 50-50. The computer should handle that easily, so no need to. Okay, so now we can see the diffuse is lighting it blue from one side, and that side isn't changing. But as we go around, the point where the light is reflecting into the camera is changing. So I can go higher up and look down, and it's kind of following me around a little bit. It's not pointing directly at me, it's pointing at exactly between where I'm looking straight at the sphere and where the light is shining on the sphere. So it's a reflection of the light. It's a reflection point. But obviously it's not an actual reflection, because that would take a lot more rendering than this is. We can see the specularity has been added here, but the specularity is white while the object itself is blue. I haven't made a variable for the specularity, but we can go ahead and... Why did this happen? We can go ahead. Is there anyone who remembers how exactly I can get rid of this? No, okay, thank you. All right. So the specularity color isn't being set through the program, but we can still go ahead and try to change that a little bit. So let's make fairly intense red specularity while we have an actual blue color. Okay, this again, this doesn't make sense as anything simulating reality, but we can do this. We can say the light that's being reflected off of this is red, but the light that it's, well, is being reflected off it differently. That is, that's scattering off of it is blue. So when we go to the other side here, we still have that point. Okay, so let's stick to white specularity. Are there any questions on this? Or do you understand why this is happening? Is the main question here. I can show you a lot of things happening there in program, but I want to make sure that we're kind of on the same page with why this is happening. It's happening because of math. That's why. Math and magic are...
What in particular is happening?
We're calculating awesome figures and vectors and stuff. Well, the idea is that we want to be able to simulate two types of light here. One of them is the light that just hits the object or scatters in all directions off of the object, and it doesn't matter where we are, we get the same amount of it. So the only thing that affects that is the normal and position of the object and the position of the light. or more particularly the direction that the object is facing and the direction from the object to the light. Those two vectors affect that. When we add the third vector, which is the vector, the direction to the camera from the object, where the position of the camera has an effect as well, then we basically take this imagined kind of perfect reflection normal, which is the h vector, which is a simulation, but we just take this halfway vector and say this would reflect this perfectly. If that is exactly parallel to the normal, we get highest intensity again there. And the reason the shine spot gets smaller as we make that power higher. So what we're doing here is we don't just take Fung and multiply that with this. We take Fung to the power of the shininess. And the higher the shininess is, because Fung is always between 0 and 1. Fung will never be lower than 0 and it will never be higher than 1. That means that by putting it to a higher power, we're actually making it smaller. So something like 0.5, if we get a Fung of 0.5 and put that to the power of 2, we get 0.25. So we're diminishing the effect of this. So the pure Fung value would be like we saw at first, equally intense like over the entire half of the sphere. But if we take a point like here where it's darker, we put it to such high a power that maybe the intensity originally was around 0.5 here, but 0.5 to the power of 20 is just almost 0. So it's having almost no effect except very close to where it would be fully 1. Obviously, in the center of this, Fung will give 1, and 1 to the power of whatever will always give us 1. So we have full intensity there. But as soon as we go a little bit away from it, to 0.9, as soon as we put that to the power of 20, 0.9 has become 0. Almost nothing again. So the higher the power on the shininess, the smaller the shine spot will be, and so kind of more intense this glossiness. So if we put it super high, set shininess to 50, 100, yeah, 150, how about that?
300.
Now again, we're seeing these effects. I really want to see if we have time to move all of these calculations into the fragment shader. If we fail at that, then no big deal, but hopefully it'll work out.
So the sphere has two shiny spots because you have two cameras.
Well, the sphere has one shiny spot when I render it here.
Yeah.
It has another shiny spot when I render it here, but it doesn't have both shiny spots in both images. No. So when I render it here, I'm using the camera that I'm looking through here. When I'm rendering it here, I'm using the camera that's straight above. So each one of these renderings will render it differently. The vertices will get different colors in each of these renderings because the position of the camera is affecting it. Alright, so what I want to do now is to see if we can actually take this into the fragment shader and do per pixel lighting rather than... So we have a very simplified model here. We only have one light. We're setting the diffuse color of the material in the light, and the specular color we're just setting to some values. So just remember that when you actually want to set up this model, you have to make a consensus decision on, am I going to have separate colors for specular and diffuse for the light, or am I just going to have one light color? Am I going to have a global ambience model and not ambience per light? I like that simplification. It's nice to use, and when we're doing the shaders ourselves, then we don't have to implement the other stuff, just implement the global ambience. But I think for the material, you really need separate specular, ambient, and diffuse values. We can maybe use the diffuse value for the ambience as well, and then just the ambience factor, the global ambience factor, will diminish that. But the specular of the material really has to be separate from the diffuse, because a lot of things will reflect white light while they actually are of a different color. Anyway, so we'll make a decision on that, or you'll make a decision on that for each of your shaders, but for now we're just using pure white always for the specular material, and we're using the light diffuse both for the diffuse and the specular. So we have Fung to the power of shininess, we have material diffuse, we're calculating this. So this stuff still has to be in the vertex shader. This here has to be in the vertex shader, so this is what we want to move into the fragment shader. So, do you understand at this point how the fragment shader works? It's super simple now. Let's open the fragment shader here. Okay. So what it's doing is it's allowing us to take variables like v underscore color that we decided just to hook up with the vertex that we're sending through the OpenGL pipeline. And we just say, after the vertex shader, we have some clip coordinates. But onto those clip coordinates, we're going to hang these other values. In our case, we hung this v underscore color onto it. And it just follows it throughout the pipeline. And any effect that is had on the clip coordinates themselves don't affect that color. Unless if it's clipped as part of a polygon, and it has to, the polygon kind of has to be shortened, the color needs to be calculated up. But all this happens through these linear interpolations between values. So based on linear interpolations between the positions of the vertices, we also do linear interpolations of these extra variables. And finally, when the rasterization figures out every single pixel that is affected by this polygon, it finds these linear interpolations between the vertex coordinates, and it applies those same linear interpolations to, in our case, the color, meaning that we get the gradient color over everything. And actually, if we go through to sphere graphic here again and make it really small again, or make it really the detail small, so we can see that sometimes right here we can see that we get almost full intensity on the specularity in this vertex. Then there's a vertex here and here that gets a different color, and we can see how OpenGL simply linearly interpolates from this color to these colors over all the pixels that are affected by this triangle. So this polygon has 3 vertices. This vertex will go through the vertex shader. Then this polygon goes through the vertex shader, and we hang a color to it. And this vertex goes through the vertex shader. So 1, 2, 3 vertexes, each on their own through the vertex shader, and each one gets a different value for v underscore color that follows it throughout the pipeline. During rasterization, OpenGL will say all of these pixels here that are affected by this, they will get a color based on some linear interpolation or some weighted average between these vertices. That will be multiplied with all the colors, and we get a weighted average of the color in this case. But OpenGL doesn't care if it's a color that we're sending or if it's any other data. We can send any numeric data, and it will have that same effect on it. In this case, it's a color, and we can see very easily how this gradient happens. Actually, on the projector, you can't see it as nicely as I can on my computer, but here it's a bit better. So you see that this is more intense than this and this, and we have this kind of even gradient over this polygon. Okay, and all of these polygons are affected more or less similarly. So what we want to do is now we want to not calculate the entire color here, here, and here and get this lame gradient, because as soon as we go here, full intensity should be happening here, right? Full intensity for specular should be happening here, but there's no vertex there. So nothing happens, and suddenly there's no specular shine point on this object. We fixed it earlier by just making more vertex detail in the surface of this object. What we want to do is kind of to be able to calculate more for the pixel. So not right now we're getting a color here that doesn't have specular intensity, here that doesn't have specular intensity, and here. That gradient between them just gives us this flat color. And since there's no vertex here, we're missing the actual spot where the shininess is happening. Okay, so this is the idea with the fragment shader and the vertex shader. So if we want to take these calculations and move them into the fragment shader, what can we do? Seriously?
Send the data over.
Okay, we need to send other data through. So we don't want to send the color. Now what we want to do is we want to calculate the color here. So if I simply take this and say, here's my lighting, I'm just going to put that into the fragment shader. All of this data here, where do I get that from? Magic. Okay, we want to calculate some data instead of the color and let OpenGL send that through its nice process of linearly interpolating over all the pixels, right? Okay, so light position and position, these are things we're using in the vertex shader. So let's say we still need to do this in the vertex shader. This is something we do here. Let's call this preparation for lighting. Okay, we still need to do this because this is data that we have here in the vertex shader. So now we're not going to have any V color. We're not going to have any varying V color. What are we going to send over instead? What are we going to say? This is what we're going to calculate for the vertex. And then we're going to allow OpenGL to linearly interpolate that over the pixels. And then we're going to calculate the color in the fragment shader. What variables do we want to have varying?
Yes, like shininess. Different shininess over the gradient.
Well, the shininess itself is kind of a color factor, so we're going to use that. So what we're actually going to do here is we're going to take these things, light diffuse, and material shininess, and we're going to put those into the fragment shader. Luckily, we don't have to change our code at all. They have the same names, and the shader program will still recognize them, whether they're part of the fragment or vertex shader. So these things are constants, or not constants, but variables or part of the static state machine that we're making of our shaders. So we just put this data in. Here we have the position data and all the kind of geometrical data. So we're going to calculate the color on the other side. Question is, well, okay. So what we're going to do is we want to take the geometrical data that we need to calculate these intensities, and we're going to use that. So what we're going to do is we're going to take the vectors that we use in here, which is the normal, and the vector S, which is the direction to the light, normal, and the vector H. And what happens then, if we, well, no, we can't actually run this right now. If we imagine, for instance, let's go into OneNote here, which is always super fun. Okay, if we imagine now that we have a polygon here, and I'm always drawing these polygons. Always drawing these polygons just as like kind of sections of them, flat images. So let's imagine what we had earlier, where we basically had a normal here, we had a normal here, and we had a light. Let's imagine we had a light here, and we had our camera eye here. Okay, so right here we would have gotten a nice H that would reflect directly, and we would have gotten high intensity. But there was no vertex here. Instead, we're getting direction to the light here and the camera here. We're getting the H vector that's somewhere around here. Sorry. H vector is somewhere around here. So the H vector and the normal, the angle between them is low enough that we don't get any specularity. On the other side, the same thing. We're going to get the H vector that's somewhere around here. And so both of these vertices, if we calculate the color there, we'll get almost no shininess intensity. But if we take the H vector that's here and this H vector that's here and send them through varying, then we say, okay, for each pixel that will be affected here, each pixel along this polygon, they'll be linearly interpolated. So somewhere around here, this vector, which is being linearly interpolated from this to this, will become first this. Somewhere around here, it'll actually linearly interpolate into a vector that's pointed straight in this direction. We also take the normal. So the normal is here, and the normal is here. If we take those and linearly interpolate them from here to here to here to here, somewhere around here, there will be one pixel where the linear interpolation between this normal and this normal will be parallel to the linear interpolation between this h and this h. So this never happens in the vertices, but at some point in the pixels between, we'll end up with this. Does this make sense? So we're going to take the normals. It's hard to draw this entire thing. Yeah, I have a touch screen. But, well, it's definitely better than using the mouse, but it'd be great to actually be an artist and have a background pad or something, but you know, can't have it all. So okay, I'm going to try to draw this. Imagine this again. Now let's just imagine this with one normal. Let's imagine this for the diffuse light now. We have a light here, and the normal for this vertex is here. The normal for this vertex is here. In this vertex, if we take this angle here, it'll give us some intensity. Okay, that's great. But this intensity will be rendered flat over this entire polygon, right? So what we do instead is that we say we're not going to calculate the entire color here and then get the flat interpolation between them. Instead, we're going to say I'm going to take the normal itself and the direction to the light, and I'm going to put those up as varying. Then for each pixel, there will be a linear interpolation between those vectors used. And somewhere around here, we can imagine that the direction to the light will be a linear interpolation between this vector and this vector, which is somewhere around here. And here, the linear interpolation between this vector and this vector will be somewhere around here. So the angle is a little bit smaller now. Even though we never had an actual vertex where this data was like that, we're taking these vertexes and these normals, and we're linearly interpolating them until right around here, the linear interpolation between this vector and this vector will be something like this. The linear interpolation between this vector and this vector will also be something like this. So suddenly, we have a pixel where they're parallel, and we get full intensity on the diffuse light, even though we never had a vertex where that happened. And that's the idea with the fragment shader.
Fake vertices.
Or fake data. So yes, we don't really have true vertex data to calculate this, but in the fixed pipeline, or in kind of per vertex shading or Gorod shading, we say we have these vertexes and we calculate everything there, and then the best approximation that we have is linearly interpolating the color over the entire polygon. And so we get this flat color over it. It's not flat, it's still a gradient. And for diffuse light, usually it looks good. But when the specularity comes into account, it gets weird. And also, even for diffuse light, we can make a lower polygon model look nicer if we can do these calculations per pixel. So what we're going to do now is, instead of calculating the color per vertex and linearly interpolating that, we're going to calculate these three normals that we need. We're going to linearly interpolate those normals, and then we're going to calculate the actual color for the pixel in each pixel. Let's just do it in the program and see what it looks like.
Is this cheaper calculations?
No. These are more expensive calculations.
Than making more vertices?
There will be a sweet spot somewhere between that. So rendering more polygons with cheaper lighting calculations versus rendering fewer polygons but with more expensive lighting calculations, there will be a cutoff. It's a trade-off. But in the end, for the last 10 years at least, what people have been going for is lower poly models with per pixel lighting. And then for the last 10 years, computers have also been getting better and better and better, and graphics hardware better. So now actually computer games have pretty high poly models also with per pixel lighting. So, you know, best of both worlds in this great year of 2015. Okay.
Calculations don't take GPU or...
Yes. The shader if you have a good graphics card, then the entire shaders will be run on the GPU. But it depends on drivers for the graphics card. If you have a bad graphics card, then your driver will have to run it on your CPU instead. But not a lot of that happening anymore. Okay, so we have 10 minutes here, and we're going to try to see if we can get this to work. So now we're going to say we're going to have this varying v underscore normal. We're going to have the varying v underscore s. And we're going to have the varying v underscore. We could go with v, but we could also, I think it wouldn't matter if you go with h. So let's just try that. I haven't done extensive testing to see if there's a difference between calculating h beforehand and using that, or sending v over. I've tried both, just depends on how you feel. But it means that this single line here, which is not very expensive, but it means this will be done per vertex rather than per pixel, so a little bit cheaper to calculate h. Everything you can do in the vertex shader will make it cheaper than doing it in the pixel shader or in the fragment shader. But on the cost of, in some cases, that it won't look as good. Okay, so we set these varying, okay, all varying variables must be declared in both the vertex shader and the fragment shader, because we're setting them in the vertex shader and we're using them in the fragment shader. So they have to have the same names, and you have to make sure they're both set there. So now what we're going to do is we're just going to say v underscore s equals this, vec for v equals this, and v underscore h equals v underscore. I hope we can use the varying like this in here. I wasn't going to do that. So, okay. So now we're making a varying for this, and we also need one more thing, which is v underscore normal equals normal. Or we could actually just do that. We could just do that in this line, because as soon as we've sent the normal, either done lighting calculations with it or sent it into the fragment shader, then we don't really need it anymore. So we're not using this, for instance, is entirely unnecessarily to actually send the normal through the view matrix when we're doing the lighting calculations in global coordinates. When we were doing lighting calculations here, like the base shader that I gave you, doing it in I coordinates, then we needed to send the normal through the view matrix as well. So okay, we got the normal varying, we got the s vector, and we got the h vector. So this should work. The fragment shader now does these lighting calculations, except now we have to use v underscore s. Here we need to use v underscore h. V underscore h. It'll be a miracle if we can just pick all this code in and then just works. And now we don't do v underscore color, we just do gl frag color equals this. Take this line out. And let's see what we're doing here. Yeah, this has to be v underscore normal as well. Light diffuse, material diffuse, volume, material shininess. Well, might as well try it. Check that out. If you look at the edges here, you can see how low poly this sphere model is. We're still getting this absolutely perfect shine sphere there. Yeah, round of applause. Thank you, thank you. I'll be back next week, same time. This is beautiful. And yeah, this we weren't seeing earlier, because we know that we just have vertices here, 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 and here. So the earlier version that we had, we weren't really seeing any shininess on the pyramids, except as kind of where the intensity was most, we saw entire tiles lit up. It's a little bit more intense, but here we're seeing it actually as it looks like the actual light source is reflecting in the pyramids themselves. I'm actually impressed. Sweet. Maybe I should prepare better for this so I actually know what I'm expecting to get. and we can see exactly how the shine spot is moving around. The position of the camera is affecting where that shine spot is, whereas the diffuse isn't moving at all. And now let's do something fun.
Wait, how did you set the light location?
I'll get to that just after I do this. Whoa, what happens there? Whoa, that bloop isn't happening now. It's from here.
Oh, yeah,
It's, yeah, if I go closer. I'm not even going to try to explain exactly what's happening there. It's just part of kind of the shininess going around there. So we have this light source moving around. Maybe it's the shininess on the inside or something. There might be things that I'm not taking into consideration, backsides and stuff. We have to make sure that all these calculations are perfect. But I think it's good enough for the most part. And we're changing so many colors and stuff. So yeah, I look at, the question was, where are we actually setting the light source? So in the game class here, I am setting the light position here. And earlier I was just setting it to a fixed position. So let's try that again. Okay, what I'm doing, now I'm just changing the color of the light, but the position is fixed. Okay, I'll show you how I'm doing this. So I'm setting the light position here in just a function that I made on my shader class. Inside the shader class, set light position is exactly the same as set eye position and light diffuse and material diffuse. I'm calling GL uniform for F, and uniform for F is a function that is basically telling OpenGL, I want you to contact your shader, and I want you to put this data into a specific variable there. So 4F means that it's 4 floating point numbers that you're going to be putting in. So it means that it's a vector 4 that you're putting into. Here I'm using GL uniform 1F. Here I'm using GL uniform matrix 4F, which means it's a 4 by 4 matrix where I'm putting this data in. This matrix data here, this float buffer. So what I'm doing is up here I've told OpenGL I want the location for a uniform variable. So where is U model matrix? Give me some integer, and from now on, after you've given me this integer, I can use this integer as a pointer to tell OpenGL this is where I want you to put some data. So if we look at the light position again, U underscore light position, which is in the vertex shader, U underscore light position is just a variable here. I declare it here. I set values to it by telling OpenGL I want the location of this data, this variable that's called U underscore light position. So here you need the variable name from the shader in that text string. Here you just need some integer variable that you make yourself to store the pointer. Then when I want to put data in there, I say I'm going to call GL uniform 4F, telling OpenGL here is the pointer to a specific variable in the shader that I have, and here is the data that I want you to put in there. So I've asked you for where U underscore light position is, and I've stored what you gave me in an integer called light position location, or light posloc. And then I call GL uniform F with that pointer that you gave me and the data I want you to put in there. So now we can call this as often as we want, but to make it a little bit clearer, rather than having these GL uniforms all over our code, I built this shader class, and the shader class has these set eye position, set light position, set stuff. And so in our game class, I go ahead and just say, I call the shader with all of this data. And you can see that I'm also doing this with the matrices. Now, rather than saying I'm going to do cam.setShader matrices, I've now taken the camera and I've made functions on the camera that just give me the matrix. I build the matrix in the same way, but I just return the buffer. So I have get projection matrix, I have get view matrix here, and I have the same thing on the model matrix. And now I say shader set projection matrix, orthocam get projection matrix. So I'm just allowing my data to flow from my program to my shader, rather than taking these location variables that the shader gets. You can do it either way. I just feel that if we get all these location variables from the shaders, and then start kind of sending them all over the place for everyone to work with, your code will just be a little bit more complicated.
This is for the second part.
Yes, this is for what we call assignment 4, I think, the second part of the assignment. Then you want to build some kind of shader. You don't need to have a very complex shader model, just so that it has more than one light. You need to implement that. And the main thing of this is the report that you return to me, where I actually want you to go both through the shader in general and also just through the code of your shaders and explain to me what you're doing everywhere. So it's more about you being able to explain what the shaders are doing, rather than your shaders necessarily having to be super complicated. I want them to have more than one light, and I want them to have some distinction between, shining, specularity and diffuse, and you to be able to work a little bit with that. But rather than going into a hugely complicated shader model, I rather want you to make something that works, make something that you can showcase in your program. So if you have a simple shader setup that can allow for 3 lights, and you can put those 3 lights into your program, and you show me that they're working, and then I just, the main thing is that you can explain what this is doing. Just mainly for me to know that you didn't just kind of take some shader code, put it in there, cross your fingers, and hope it wouldn't crash, and when it worked, you just returned it to me. I want you to explain what the shaders are doing. So yeah, that's on the project. So there's one place actually, since we were talking about this idea that I'm trying to keep these light position locations private in the shader class, there's one place where I allow this to be sent out, and that's the attributes themselves, which is the position location, which is the vertex data that we use for the vertex lists, and the normal locations. And the reason I do this is because if we look at the sphere graphic here, so the sphere graphic sets its vertex attribute pointer, and it has this vertex pointer which it gets from the shader, and it has its own vertex buffer. So we basically have to decide now, do we want to send this vertex buffer and everything with it into the shader, or do we want to get this location pointer from the shader? Either one needs to kind of send its data, so you just have to decide which is more clear for you and less complex. You could just as well implement and that would actually be a nice way to do it, implement a draw function on your shader. And that draw function would take all these variables. That is the type, the buffer, all of this stuff if you need it. If all of it's the same, like all of its 3D vertices, you can hard code this into that. And then you won't have to send the vertex pointer out into this. But then everyone who wants to draw something needs to actually have access to your shader instance. But the way I did it, only the game needs access to the shader instance, and then it takes data from that and sends to the sphere graphic, and it takes data from basically all of the lights and that stuff and sends into the shader. All right, so I think that's enough for now. If there are no questions or anything we want to see again, then I think we're good. All right, thank you. See you next week, and have a good weekend.